Hello everyone. This is the first of a series of videos dedicated to stereochemistry and ring formation. In these videos, I will be discussing some of the key factors that affect the stereochemistry in a reaction. I will also be discussing some ways to control stereochemistry when performing a reaction, and specifically looking at acyclic systems. There will also be a part of the videos dedicated to ring forming reactions, both the key factors that affect a reaction that involves the formation of a ring, and also I will be discussing something called Baldwin rules, which can be used to describe and predict whether a particular ring forming reaction will be more or less favored. These videos are based on Chapter 6 of Organic Synthesis by Michael Smith, specifically Section 6.2, which is dedicated to stereochemistry and acyclic systems, and Section 6.6, which is dedicated to ring formation. So what sort of factors do we consider when we are thinking about controlling stereochemistry in a reaction involving acyclic systems? Well, we need to think about something called regioselectivity. We need to think about retention versus inversion of configuration when we are working with a compound that already is an stereoisomer. When you're looking at double bonds and triple bonds, we also need to think about cis-trans selectivity. And again, in addition, reactions involving double or triple bonds, zinc anti-selectivity. And finally, we are also going to be looking at chelation effects by heteroatoms that might help you control the stereochemistry to produce a specific isomer of interest. So regioselectivity. Regioisomers are compounds that have the same empirical formula, but the groups or atoms are positioned at different carbons. So for example, if I draw these two aldehydes and add one methyl group in the second carbon or in the third carbon, those two compounds are regioisomers. We talk about a reaction that will generate one specific regioisomer as the main or the major product or only product as being regiospecific or regioselective. And one thing we need to take into account when generating a regioisomer, especially if we're going to do a reaction on an addition in a double bond, is the Markovnikov versus anti-Markovnikov addition. So what do I mean by that? Just as a reminder, Markovnikov and anti-Markovnikov additions are related to addition of in a double bond. So if I have, for example, this compound that has a double bond, and I make it react with hydrogen bromide, in that first step, the double bond will attack the hydrogen and liberate the bromine ion. And which carbocation will form? Well, the most stable carbocation is the one in which the positive charge is generated in the most substituted carbon. So when the bromine enters the molecule, it will substitute. Substitution will happen in the most substituted carbon, and that is what we call with Markovnikov addition. In an anti-Markovnikov addition, the substitution is the other way around. And you can have that if you use, for example, radicals. So by generating radicals, for example, if we have the same compound and we do the same addition, but instead of just using hydrogen bromide on its own, we add peroxides, then you generate the radicals, the bromine radical, which can attack, and it will attack this carbon, and that is because the most stable radical you can form with this carbon compound is here in the more substituted carbon. So when the hydrogen comes in, it will enter enter in this carbon, and you will have the different a different stereoisomer. in which the substitution, the bromine, have gone into the less substituted carbon. So you can have Markovnikov and anti-Markovnikov additions and put those substituents in the carbons that you desire them to go, depending on what the conditions of the reaction. So an acid catalyzed addition, for example, to make an alcohol, if you add water to an alkene and with using acid as a catalyst, then you will produce the Markovnikov product. So the OH will go into the more substituted carbon. However, if you use a radical formation for example, using hydrogen peroxide, then you can form the anti-Markovnikov orientation. So the hydroxyl go into the the least substituted carbon. And then afterwards, if you, instead of the alcohol, you want to produce the bromine compound, as in the previous case, you can just use phosphorus tribromide and generate the anti-Markovnikov addition of that bromine. These two reaction mechanisms, if you follow this route, you will get the Markovnikov addition of that bromine. If you follow this route by using a radical an addition using radicals, you will produce the anti-Markovnikov orientation. So you can control the formation of one or another of the regioisomers depending on the conditions of the reaction. Something else we need to take into account is retention versus inversion of configuration. So if you already have a stereoisomer and you are doing, for example, a nucleophilic substitution, will you produce the same stereoisomer, the stereoisomer with an inversion of the stereochemistry, or maybe a racemic mixture, a combination of both? SN2's reactions, because they are they depend on the forming of this intermediate of reaction, proceed with complete stereochemical inversion. So your product will have the opposite stereochemistry as your reagent. In SN1s, because the intermediate step is a carbocation, in general, that means the stereochemistry is lost, since the nucleophile can attack, in theory, it might have some preference, either at the top or at the bottom. And you end up with a complete or at least partial racemization of your product. So you get both possible stereoisomers. However, it is possible to control configuration, stereochemical configuration in a nucleophilic substitution, both keeping the original configuration or if it's necessary, inverting the configuration. And that is by doing the substitution using, for example, thionyl chloride. This is the formula of thionyl chloride, and this is a mixture of thionyl chloride and pyridine. So using thionyl chloride on its own will result in a retention of the configuration. So the substitution, you have here an hydroxide, you have ended up with a product that has a chlorine atom, but they have the same configuration. If you mix thionyl chloride with pyridine, then because of the way the adduct form, you end up with an inversion of the configuration. So here is your hydroxyl group again, and when the chlorine atom is added, when the substitution takes place, you end up with a chlorine atom in the opposite configuration. So it is possible to control the configuration, either keeping, retaining the original configuration, or inverting it, depending on the desired product. Another example of a reaction that can help you control the configuration of a particular functional group, in this case inverting the configuration, is the Mitsunovi reaction. And it can be used to invert the stereochemistry of a hydroxyl group of an alcohol. So if we look at these two compounds, 89 and 90, they are identical, and the only thing that changes is the configuration of that hydroxyl group. They are opposite configurations.
So what the Misnovi reaction is, it's a substitution in that hydroxyl group. The first step is to convert your hydroxyl group, which is a bad leaving group or poor leaving group, into a better leaving group. And that's by using diethyl azo dicarboxylate, DED. And that makes your hydroxyl group into an ester. Esters are much better leaving groups than hydroxyl groups. So then the reaction can proceed by using a nucleophile, a good nucleophile, which, for example, in this case, lithium hydroxide. So there's a nucleophilic substitution, and a new alcohol is formed, and it has the inverse configuration to the original alcohol. So this is another example of how to control the stereochemistry of a particular functional group, retaining that functional group, that specific functional group, hydroxyl, but changing the configuration.